So it's a great pleasure to have Martin Kerin, who will tell us about a potpourri of non-negatively curved 7 manifolds.
Thank you very much, Renato, for the introduction and for the opportunity to give this talk. Thanks also to you and the organizers of the virtual seminar on geometry with symmetries for accommodating this joint meeting as a result of technical difficulties last time around. Hopefully I get beyond the first slide this time. As Renato said, I want to talk about non-negative curvature in dimension 7, and this is joint work with Sebastian Goette in Freiburg and Ravi Shankar from Oklahoma and the NSF. And of course, got to get the correct buttons. Something is not working. There we go. Non-negative curvature is one of the most basic concepts in Riemannian geometry, and yet surprisingly, it's not that well understood. So we have the famous Soul theorem by Kerin and Goette for non-compact, non-negatively curved manifolds. And this says, of course, that a non-compact, non-negatively curved manifold is diffeomorphic to the normal bundle of some closed submanifold. And this closed submanifold is totally geodesic and hence also has non-negative curvature. So in some sense, closed manifolds with non-negative curvature are the most important. And yet, we really don't understand anything or much about these at all. Part of the problem is that there are a few examples, or really I should say there are a few constructions, and all of them at some level depend on two basic facts. The first is that Riemannian submersions are curvature non-decreasing, where remember Riemannian submersion is a smooth submersion that is an isometry orthogonal to the fibers. And in particular, this means so the curvature non-decreasing property means that if you have non-negative curvature upstairs, then you get non-negative curvature downstairs. This comes in useful and is often used in the situation where you have a free isometric group action on a manifold with non-negative curvature, and then you take the quotient by this action and you get an induced metric with non-negative curvature on the quotient space. So that's where this usually gets used. And the other basic fact is that compact Lie groups admit a bi-invariant metric. And of course, this is maybe the first curvature computation that everybody does when they study Riemannian geometry, is to show that compact Lie groups admit, that the bi-invariant metric on a compact Lie group has non-negative curvature. Okay, so the strategy here and in many other areas of mathematics, of course, is to try and build highly symmetric examples, understand that situation, and then try to reduce symmetry somehow. So in the case of non-negative curvature, we have a large class of very symmetric spaces, namely the homogeneous spaces, where we have a homogeneous compact Lie group action. And you can think of reducing symmetry here as saying, well, why don't we do something different and introduce the concept of a biquotient. And for those of you who don't know what a biquotient is, instead of taking a subgroup of the group G, you take a subgroup of G cross G and you let it act on G on both sides. So it acts on the left by H1 and on the right by H2 inverse. And you don't get freeness automatically here, so you have to check. So not every subgroup H will act freely, but those that do will give you a new manifold with a non-negative curvature. And interesting topological types beyond those of homogeneous spaces already occur in this situation, where there's very little symmetry left over. So for example, the first biquotient to appear in the literature, as far as I'm aware, was that of Gromol and Meyer, who showed that a certain exotic 7 sphere admits non-negative curvature by writing it as a biquotient. Okay, so another way to reduce symmetry is to, rather than allow transitive actions, allow large actions, but not transitive actions. And the first maybe case of this is what's called cohomogeneity 1. So for me, a cohomogeneity 1 manifold is a closed manifold which admits a compact Lie group action so that the orbit space is an interval, and for convenience I parameterize it by as -1 to 1. And the picture you should have in your head is of rotating a sphere around an axis by your group action. And of course, the orbit space here is an interval. And you see that there are two special orbits corresponding to the endpoints of the interval. These are called singular orbits. And they're homogeneous spaces, and each comes with its corresponding isotropy group, so K plus and K minus. Then if you take a normal geodesic between these two singular orbits, this corresponds, of course, to the interval. And for every point on the interior of this normal geodesic, you take its orbit, and it turns out that all of these orbits are diffeomorphic, and if you are taking the base point along this geodesic, then all of the isotropic groups are the same. So this isotropic group, we call it H. And of course, there's a relationship between these three isotropic groups that appear. Namely, we have a group diagram ordered by inclusions. And you see that I have decorated it with these spheres. And that is because, just as in the picture, this looks like a union of two disks centered on the singular orbits. Well, this happens in general for cohomogeneity 1. You have the normal disk bundles to the singular orbits, and they get glued along the middle, and the middle is a copy of this so-called principal orbit G mod H. And in order for that to happen, that means the sphere bundle has to be G mod H. And the condition for that to happen is that these isotropy groups have the quotient to give spheres. And so this L plus and L minus correspond in some sense to the codimension of the singular orbits. So for example, if I have circles in this picture here, then that corresponds to codimension 2 singular orbits. And this is a situation that we like to have for reasons that I will explain in a moment, namely now. So Goette and Tiller showed in 2000 that if you have a cohomogeneity 1 manifold with codimension 2 singular orbits, then there exists a G-invariant metric with non-negative curvature. And this turns out to be very powerful and very useful, and is essentially the only curvature computation that we will do in this talk. So we get it for free from this result, essentially. So what did they do with this result? And how did they apply it? Well, they showed that all principal S3 cross S3 bundles over S4 admit a cohomogeneity 1 action by S3 cross S3 cross S3, and I purposely put the last two S3s in brackets here because this is supposed to be the principal action. And the codimension of the singular orbits for this action is 2, which means by their theorem, you get a metric with non-negative curvature. So let's look at how they did it. Well, they started off with the cohomogeneity 1 diagram for S4, and excuse for a moment the fact that this S3 is off to the side. There's a reason. So this is the cohomogeneity 1 diagram for S4 with respect to an action by S3. Q8 here, so I'm thinking of S3 as the unit quaternions. Q8 here is the quaternion 8 group consisting of plus minus 1, plus minus I, plus minus j, plus minus k. Pin 2 and pin 2 are isomorphic. Pin 2 is a one-dimensional compact Lie group consisting of two components. The identity component is the circle in the complex plane, and the second component is the image of this circle under multiplication by j. And pin 2, this is just a suggestive notation. So this is really just saying switch the roles of I and j in this group. So it's really just another copy of pin 2 inside the group. And I just want to point out as well, the singular orbits here, just because I'll mention it later, are copies of RP2. So we're S3 quotiented out by a circle and a Z mod 2. Okay, so these are RP2s. So codimension 2 singular orbits. And what Goette and Tiller showed is that you can actually lift this codimension 2 cohomogeneity 1 action to the principal orbits by adding on an extra 2 factors, as I said. In the end, you spread the quaternion 8 group across all 3 factors by taking the diagonal subgroup, and you spread the pin 2 and pin 2 groups into the other 2 factors by allowing some slope in the circle. Okay, and I'll tell you more about the slopes in a moment, but for the moment, all you should remember is that we maintain codimension 2 singular orbits, and we have this group diagram. Okay, so So using this, they were able to prove that all principal S3 crosses, they get all principal S3 crosses 3 bundles over S4 by this method. And so all of these manifolds P10 admit an S3 crosses 3 invariant metric with non-negative curvature. And once you have principal bundles, of course, the next thing you do is you build associated bundles. And that's what they did. They built the associated, so the unique associated S3 bundle to each of these principal bundles. And you automatically get non-negative curvature in this case as well, almost automatically. So you take this cohomogeneity 1 action, or sorry, the metric, cohomogeneity 1 metric with non-negative curvature on the cohomogeneity 1 manifold. You take the round metric on S3, take the product, and then you divide out by the diagonal of the principal action. So it acts on both of these. And you end up with a metric with non-negative curvature on an S3 bundle over S4. And you get all S3 bundles over S4 in this way with a metric with non-negative curvature. And of course, maybe some would say the most interesting thing about this is that you get all of the Milnor exotic spheres as a subfamily within the S3 bundles over S4. So these are the exotic spheres that Milnor discovered when he was studying S3 bundles over S4. So they all have a metric of non-negative curvature. And let me just remind you a little bit about these manifolds. So Milnor discovered them in the 50s. And soon afterwards, a combination of the work of Milnor and Smale showed that there are 28 oriented diffeomorphism types of manifolds homomorphic to S7. But if you're interested in curvature, then you don't really care about the orientation. And so there are 15 unoriented diffeomorphism types of manifolds homomorphic to S7. A year after this, this classification was concluded, or this enumeration maybe was concluded, Eels and Kuiper were able to write down an invariant which classifies the exotic 7 spheres up to oriented diffeomorphism. And in particular, they showed that the Milnor exotic 7 spheres give 11 of these 15 diffeomorphism types. Okay, so then there are 4 exotic spheres, which at this stage after the work of Goette and Siller were unknown, or it was unknown whether they admit non-negative curvature or not. And these guys, if you're enumerating the spheres with these Kuiper invariant, these correspond to the invariants which are plus or minus 2 mod 7. So elements of Z mod 28, which are plus or minus 2 mod 7. And here's a list of them, just to save you having to think about it. And you should just notice, of course, there are 8 of them. Each one occurs with 2 different orientations. So 5 and 23 are the same diffeomorphism type, but different oriented diffeomorphism types. Okay, so part of this talk is going to talk about these non-Milnor exotic spheres. So that is sort of the state of play. But in order to get there, we want to look at these manifolds that Goette and Siller studied, these S3 bundles over S4, and change the way we look at them. So maybe the most suggestive way I can do this is to say, well, look at the fiber, the S3, and we'll rewrite it as a homogeneous space, S3 cross S3 mod the diagonal S3. And now you see that this S3 cross S3 acts transitively on the fiber, and there's a diagonal S3 left over, but it has to do something. And what does it do? Well, it gets whipped around and it acts on the cohomogeneity 1 manifold. And so these manifolds that we built as associated bundles can really be thought about as taking quotients of our cohomogeneity 1 manifold, and the action that we're quotienting by lives inside S3 cross S3, and it's sitting inside this diagonal subgroup is actually in the last 2 factors. In the first factor, nothing happens. Okay, so what does this mean? It means that we have a cohomogeneity 1 manifold. We quotient out by a sub-action of the cohomogeneity 1 action, which is free. So we're quotienting, if you follow through what it's doing to the orbits, you're actually quotienting all of the orbits by a free action, and you end up with biquotients. And so each of these groups, Q8, Pin2, and Pin2, sits inside S3 cross S3 cross S3. I'll just call them all U for convenience. And then an element of U acts on S3 cross S3. So we're taking into account the fact that we're pushing out the diagonal S3 here as well. And what does it do? Well, it acts on the right of the Q1 by the first coordinate, and on the second coordinate, it acts on both sides. So that's what it does. And just because it'll pop up later, notice that there's an S3's worth of symmetry left on the left-hand side of the first coordinate here. And this is actually going to give an SO3 symmetry group, because plus or minus 1 always acts trivially under on each of these biquotients. So there's a leaf-wise SO3 action that gives a global SO3 action. Okay, so this is nice. This is a nice way of thinking about these manifolds as well, because it tells us that we still have this nice decomposition of our manifold as a union of two disk bundles. And for topological reasons, this is very useful. And we make strong use of it in our work. Okay, so I told you I'd tell you a little bit about the slopes. So in the Goette and Ziller picture, where they were talking about S3 bundles over S4, in order to get the S4, remember the principal part of the action is in the last two factors. So the ones here are coming from the action on S4. And when they lift to the principal bundles, you get 4 parameters worth of freedom here for what you can do. And that allows you to get all S3 cross S3 principal bundles over S4. But of course, now we don't care about S4 when we have this description of these manifolds. We don't care that they came from taking bundles over S4. And so this suggests that there might be a much larger family in the background. And indeed, that's the case. Well, what are you going to do? You're going to change these ones into some other parameters. And so that's what we do. We allow 2 more parameters. And these GCD conditions are so that this diagonal S3 action is free on the cohomogeneity1 manifold you get. So think back to the cohomogeneity1 picture we had. These are the slopes of the 2 pin groups in there. There's a perfectly nice cohomogeneity1 10-dimensional manifold. In order to get a 7 manifold, you need freeness of this diagonal S3 action, and the freeness condition is given by these 2 GCD conditions. And notice if A1 and B1 are both equal to 1, then this is an empty condition, and that's exactly the situation that Goette and Ziller were in. So for free almost, just by looking at it a little differently, you get a large family of 7 manifolds, which still have non-negative curvature. I told you that there's SO3 invariance there. They're 2 connected, so they already sort of look like S3 bundles over S4. Their cohomology even looks like that of an S3 bundle over S4. Where I just want to point out this N, which depends on the parameters A and B, it's allowed to be 0. So you even get manifolds that look like S3 cross S4 appearing. But in this talk, we're really only interested in those which are rational spheres. And these manifolds all admit a Seifert vibration with generic fiber S3, where the leaf space is an orbifold S4. So in some sense, they're orbifold S3 bundles over S4, and the orbifold singularities are pretty mild. So remember I told you in this cohomogeneity1 picture for S4, the singular orbits are RP2s. The exact same thing happens here. You get an S4, you have 2 copies of RP2 in it, and the orbifold singularities are in the normal circles to these RP2s, and the problem is that they're too short. And they're too short exactly by a factor of A1 or B1. Okay, so it's still a pretty nice almost bundle, but you just have to worry a little bit about these orbifold singularities downstairs. Okay, so they really do look like S3 bundles over S4. These things. So that's all I want to say about the theorem. Now I want to move on to corollaries, and this is what I spend the rest of the time talking about. So the first is that we get all exotic spheres as inside this family of manifolds M7AB. So we get the non-Milnor spheres in particular. So this already says you're getting manifolds which are not S3 bundles over S4. we, in fact, get infinitely many manifolds M7AB with non-negative curvature, which I call non-standard for reasons you'll understand a little later. And by this, I mean that they're not even homotopy equivalent to an S3 bundle over S4. So this is pretty weird when you look at the theorem. The theorem says, well, these things are pretty much S3 bundles over S4. But it turns out you get very strange spaces in this family as well. And this is the first sort of scenario like this that has been seen in non-negative curvature, that you get such bizarre spaces with non-negative curvature. The third corollary is that there are, in fact, infinitely many 7-dimensional fake length spaces with non-negative curvature. Again, this at the time we observed this was the first example of fake length spaces with non-negative curvature, ruling out some, if you sort of discard some homotopy RP5s, which were observed by Goette and Dearth. But in hindsight, when I was preparing this talk and I was looking around a little bit, it turns out that if you look at the Brieskorn 5 spheres, you can also build finite cyclic group actions, isometric finite cyclic group actions on those. And so in the same way that Goette wrote down homotopy RP5s with non-negative curvature, you can also get Brieskorn via the Brieskorn method in dimension 5 some fake length spaces. But that doesn't appear in the literature anywhere, and it's using ideas going back to the 60s, I think, with Orley. Okay, so we get these 7-dimensional fake length spaces, and we also get at least 28 oriented homotopy RP7s as well. And there are infinitely many homotopy RP7s, so it's very much different to the 5-dimensional case where there are only 5 homeomorphism types, I think, or diffeomorphism types. I don't remember what it is, but it's a finite list. Okay, so let's just look at these corollaries. So let's start with the exotic spheres. So what we have to do is find some family within our 7 manifold, family of 7 manifolds, where they're all spheres, and then we have to compute the Kuiper invariant to determine which exotic spheres we get. But these Kuiper invariant exists for all of our 7 manifolds, and so we compute it in general. So this is what the Kuiper invariant is. And so at first glance, it looks a bit daunting, but I'll try to convince you that it's a very natural thing to look at. And from now on, I should say that we're assuming that n is not equal to 0, meaning that H4 is always going to be a torsion group for us from now on. So before I try to explain the definition of the Kuiper invariant, I just want to say that the W that appears there is some 8-dimensional compact smooth oriented spin manifold whose boundary is M7. So it's a co-boundary of the manifold M. And the way you should think about these Kuiper invariant just intuitively is that if this manifold W were a closed manifold, then the right-hand side here would be the A hat genus of W. And Hirzebruch showed that the A hat genus of closed 8 manifolds is an integer. And so if you take it mod 1, then it would vanish. So what the Kuiper invariant is measuring is the failure of this manifold W to actually be a closed manifold. And it's measuring that by throwing away the integer part and just taking what's left over. But it turns out that the Kuiper invariant really only depends on the boundary. It doesn't depend on which manifold W you choose as your co-boundary. And that goes back to the work of Milner in his paper where he discovered the exotic 7 spheres. So we're looking at manifolds that are rational spheres. So if you take rational coefficients in the long exact sequence for the pair, you'll get an isomorphism going from H4 of the pair to H4 of W. So that's this map here. It's allowing you then to pull back the rational Pontryagin classes from W to the pair, where they otherwise don't make sense. So you pull back the rational Pontryagin class, you square it to get into the top degree, and then you evaluate on a fundamental class for the pair. So that's the first term. And the second term is, of course, just the signature in the usual sense that you take an element of H4 of the pair, you square it. This gives you a bilinear form when you evaluate on the fundamental class, and this bilinear form has a certain signature, and that's what this measures. And so this is really very similar to the A hat genus even in this description. Okay, so as I said, this right-hand side doesn't really depend on W. So it would be nice, because we don't really have a nice method for finding W, it would be nice if we could write it just in terms of M. And it turns out you can do that, but you have to go via the Hepatoid index theorem. And so what we do here is we have a background metric on M, which we call GM. And for our computations, this is not the metric with non-negative curvature. So you want to choose a metric that's nice enough to allow you to do computations. So I'll explain this formula in a moment. So we have some background metric on the manifold M. And using the Hepatoid index theorem, Kerin, Stolz, and Donnelly showed that you can rewrite the right-hand side entirely in terms of the geometry of M with this metric. So what are each of the terms here? So the D here is the usual spin Dirac operator on the manifold M with respect to this metric, GM. The B is also an operator of Dirac type. It's called the odd signature operator. And this is acting on forms, and it looks like the differential times the Hodge star minus the star times the differential. And this thing is evaluated on even forms. Okay, so this is something that when you square it, again, it looks like a Laplacian. So that's the characteristic of Dirac type operators. And you see the metric coming in the Hodge star as well. Okay, so H here, this is the kernel of the dimension of the kernel of the Dirac operator. And the eta is the usual eta invariant of an operator of Dirac type. So you see it appears for both of the Dirac operators that we have. And I should say that the eta invariant is the defect in the Hepatoid index theorem due to the fact that we have a boundary. So for the Hepatoid index theorem, you start with the boundary again, you find a co-boundary W, you extend this metric GM into the co-boundary W, and the eta invariant is the defect which appears if you try to run the Singer index theorem for this manifold W with this metric, okay, due to the fact that it's not closed. Okay, so that's all of these terms. P1 here is the Chern-Bay-Pontryagin-4 form, which you get by computing the curvature form for this Riemannian manifold, and you run the Chern-Bay definition. And the P1 hat is a 3 form that has to exist because the Dirac cohomology of M in degree 4 is 0. So we cannot have cohomology, so that means that this P1 has to be an exact form. So it means that there has to be some 3 form whose differential is P1. And so inside the integral, you have a nice 7 form, and so the integral makes sense. And up to taking everything mod 1, this is the same as the Eaves-Coulter invariant that we wrote down before, and it depends only, as I said, on the geometry of the manifold M. And then you work very hard, and you compute what each of these terms are. And I don't want to go into that at all. It's really intense. But at the end, you get out this nice formula. So you get this nice rational term at the front, and then these 2 terms, dA and dB. So in this rational term, the n is the order of the H4. M is this other rational number depending on the parameters A and B. And dA and dB are the price you pay for not being a bundle. Namely, it's the price you pay for the leaf space of the Seifert vibration being an orbifold. So these are generalized Dedekind sums. They're rational functions in cosines and sines depending on the parameters. And as I said, they detect the failure of your Seifert vibration from being an actual bundle. So for the S3 bundles over S4, these terms don't appear. That's what you should be thinking. In particular, if so each half has one of these. So on the side where we had the slope A, we get one of these, and on the slide where we had the slope B, we get one of these. So if one of the halves looks like half of an S3 bundle over S4, this will vanish. In other words, if A1 or B1 is equal to 1, this will vanish, the corresponding Dedekind sum term. Okay, so this is quite complicated, but in certain situations you can compute it by hand. So I'll write down a family now where everything can be done by hand and where the non-Milnor spheres are included. So you take A to be -3, -3, 1, and B, you allow it to have one parameter's worth of freedom. And you notice we have a 1 here. So you compute the order of H4 by taking this determinant from the theorem we had previously. So it turns out that n is equal to -1, so that means H4 vanishes, which means the manifold is homeomorphic to S7. So that's at least good, but maybe you were just unlucky and rediscovered the Milnor spheres in some complicated way. So that's not quite good enough. Then you can compute these Dedekind sum terms by hand, as I said. So the first, dB vanishes because we have a 1 here. So it looks like half of an S3 bundle over S4. And the fact that we have a 3 here means that when we're talking about sines and cosines, everything is going to be something over 3. Okay, so we sort of know how to deal with third multiples of pi times multiples of a third. Okay, so these are the sines and cosines that are appearing. So everything can be done by hand in this case. And it turns out that you get that dA is -1/28. And so if you plug this into the formula for the least Kuiper invariant, you get this nice expression. I just want to point out again that remember L is 1 mod 4. So these two terms are integers. And so you have successive integers. One of them is even. So there's a 2 floating around that cancels with the 2 and the 56. So you get something over 28. So you get something that is an least Kuiper invariant as we expect. And you just choose some L's until you hit the non-Milnor spheres. In fact, there are going to be 16 different oriented diffeomorphism types in this family given by these A's and B's, but I'm just interested in the non-Milnor spheres. And the lowest absolute value of L's, which give these, are going to be the ones listed. And you see that we get all of the least Kuiper invariants that are ±2 mod 7 here. Okay, so how am I doing for time? Pretty well. So let's move on to the second corollary. Namely, that there are infinitely many of these manifolds with non-negative curvature, which are not even homotopy equivalent to an S3 bundle over S4. And so this is something that we need a different invariant for. And the invariant is the so-called linking form. And the linking form, remember, is a non-degenerate symmetric bilinear form on the torsion group, H4. But because the definition is a little more intuitive, I am going to talk about it in the third homology group by using Poincare duality. And so I'll define it like this, even though this isn't how we compute it. We compute it using the cohomology definition. And it takes values in Q mod Z. And you'll see in a moment how it's defined. But as I said, when we compute this, we use the cohomology definition. And the cohomology definition involves the Bockstein homomorphism. And we use very strongly the fact that our 7 manifolds decompose as a union of 2 disk bundles. We do lots of very subtle diagram chasing, lots of nice snake lemmas, lots of thinking about classes and whatnot. And at the end of the day, you can compute this thing, and it's quite nice in hindsight, but when you're in the middle of it, it's quite confusing. But that's the fun of it, right? So what is the linking form? Well, if you take 2 classes in degree 3, then it's given by some sort of oriented intersection pairing, and then you divide out by the order of H3 and take everything mod 1. So this is going to be in Q mod C. Now, what is this strange gamma that's appearing here? Well, this is coming out of the fact that we have torsion. Namely, if I give you a class in degree 3, it's in Z mod n, So n times that class is going to vanish, and that means that there is a four chain whose boundary is going to be n times alpha. Okay, so n times alpha has to be the boundary of something. So this thing in degree 4 then pairs up with something in degree 3. Remember, we're in dimension 7. So we have an oriented intersection of these things. So intuitively, maybe it's best to think about alpha and beta as corresponding to 3-dimensional submanifolds. Some multiple of, well, n times alpha has to be the boundary of something. So imagine you have a 4-dimensional submanifold with boundary inside M. You have a 3-dimensional submanifold. These things, when they intersect infinitely many points in general position with some signs according to orientations, and you count up these signs essentially, and that's the intersection number you're getting. So that's a good way to think about it. And you see, this is a pretty intuitive definition. It's useless though when it comes to computing the linking form, in the case of these manifolds at least. Okay, so why is this useful? Well, first, I want to tell you what standard means, and then maybe it will become clear why I was saying non-standard. So we're interested in the linking form. The linking form is standard if, now remember, it's bilinear, so we only care about what it does in a generator of the cyclic group C mod n. So if when you apply it to the 2 copies of a generator 1, it is up to sine the square of a multiplicative unit divided by the order of the group. And maybe just to make this a little clearer, so imagine that you're in Z mod 5, so n is equal to 5, then the multiplicative units are everything, of course, that is not equal to 0, and the ones that are squares are 1 and 4. But of course, if your linking form were equal to, so this is linking form of 1, 1, if it were equal to 2 over 5, the mod 1, this means that it's non-standard because, of course, plus or minus 2 is not in, oops, it's not in here. Okay, so neither 2 nor 3 are squares of multiplicative units. So this is sort of what we're thinking about with standard, in the sense of standard. Now, it turns out, for reasons which, if you keep track on the next slide, you'll see that this situation can't actually occur in this manifold M7, or in this family M7AB. So of course, these exist. There are manifolds like this with C mod 5 and non-standard linking form. We just can't get them within this family M7AB. Okay, so why is it useful to be standard or non-standard? Well, Kitchlu and Ravi showed in 2000 that adapted to our situation, the manifold M7AB is homotopy equivalent to an S3 bundle over S4 if and only if the linking form is standard. So we're really looking for situations where the linking form is non-standard, and that's why I call these manifolds non-standard. I should have said, by the way, let me go back a slide. So here, when I told you this was non-standard, the key thing that's going on in the background here, and this is what you're looking for, is that -1 is a square, mod 5. So it's a question about quadratic reciprocities, really. This is the situation you want to be in, that with respect to the order of your group, you want -1 to be a square, and this sort of allows you to split up the multiplicative units into 2 groups. You have those that are up to a sine a square, and the others. So that's what we actually want. Okay, so we're looking for non-standard linking forms, and in the back of our mind, we're thinking, okay, we want to be in a situation where -1 is a square. So I told you we computed the Bochstein homomorphism, did lots of subtle diagram chasing and whatnot, and it turns out that the linking form for our manifolds M7AB, evaluated on the generator 1, 1, our generator, is plus or minus QAB over M. So what is this QAB? Well, it obviously depends on the B's here. And then you have this the R and S, which somehow depend on the A's, and how they depend on the A's is through the Euclidean algorithm. So you find, remember we had these GCD conditions. So there exists some R and S such that, well, that are spit out by the Euclidean algorithm essentially. Okay, when you find these, and because you're taking everything mod 1, it doesn't matter which R and S you choose, and also it doesn't matter whether you have the A's in this first line and the B's in the second, or the way it is in here. So you can actually switch the roles of A and B in this, and because everything is mod 1, it all works out the same. Okay, so this is what the linking form is. Then it turns out that for every prime that is 1 mod 4, there exists a manifold in this family M7AB, so that P squared divides the order of H4 and the linking form is non-standard. So straight away, you see there are infinitely many such examples. In the paper, this is made more explicit, but I just want to say for every such prime, you get examples. Okay. So let's look at some explicit examples. So in this case, we're going to take the prime to be 5 mod 8. So it's sort of 1/2 of this family of primes. Take A to be P1 minus 3, and B to be P minus 3, 5. And notice that I'm taking A1 and B1 to not be relatively prime, so that to have some non-trivial GCD. This is essential. So you can show that in this family M7AB, if A1 and B1 are co-prime, then the linking form is always standard. So the order of your H4 has to be divisible by the square of a prime, and this is why Z mod 5 can't occur with non-standard linking form for us. If you remember back, I said it couldn't happen. This is the reason. Okay, so anyway, in this situation, it turns out H4 is Z mod P squared, and that the linking form is plus or minus 2 over P squared, and it's non-standard. Well, why? Because plus or minus 2 is a square mod P if and only if P is not 5 mod 8. And so if and only if P is an odd prime that is not 5 mod 8. In other words, if P is 5 mod 8, then plus or minus 2 is not a square mod P, which means that this term here is not the square of a multiplicative unit for either sign. So it's a non-standard linking form. And so here is a more explicit family of where you get infinitely many such manifolds, because H4 is Z mod P squared. Okay, so how am I doing now for time? Good. So let me move on and talk a little bit about the fake length spaces. So it turns out that we get a free finite cyclic group action on these manifolds as a subgroup of the SO3 action. So remember, we had this foliation of our manifold by biquotients. So if I write down after quotienting, so these coset coordinates, if you like, remember the SO3 was acting on the left of the first coordinate. So if you take a finite cyclic group inside this SO3, it acts freely and isometrically if and only if these two GCD conditions are satisfied. So that the D has to be prime to A2 plus or minus A3 and B2 plus or minus B3. And that actually implies already that D is odd, but I just wanted to highlight it, that D has to be odd. Okay, so you get, at least you can believe, maybe without doing anything else, that you're going to get infinitely many 7-dimensional manifolds with fundamental group Z mod D, just from this expression. But of course, until you show that there are explicit examples, then it might be an empty family for some weird reason. So that was for all of the M7AB. But in particular, if we're talking about homotopy spheres here, the quotients are called fake length spaces. So a fake length spaces is just the quotient of a homotopy sphere by a finite cyclic group action. And so let me focus on those for the moment, because maybe those are the most interesting and the most familiar examples. So let's look at some examples and non-examples. So remember, the family I wrote down that contained the non-Milnor spheres in the first corollary. So that I told you there were 16 possible oriented diffeomorphism types in that family. And if you check these GCD conditions, it turns out that there are no free actions for these descriptions of these 16 oriented diffeomorphism types. Of course, you can describe them in infinitely many other different ways, depending on how you choose your A's and B's, and you may get actions. So in particular, if you take the Kuiper invariant 27, you can describe it using these parameters A and B, and you can easily check that all D odd will satisfy these GCD conditions. So straight away, you get infinitely many 7-dimensional fake length spaces for all odd D. Sorry, you get a 7-dimensional fake length space for all odd D, just with this example. Here's a non-Milnor sphere with a strange description, so not from this family. And you see that there are some extra conditions on D. D cannot be 257, divisible by 257 or 109. I just want to also point out that even if D were the same, so imagine D were equal to 3. So you get a Z mod 3 action on both of these. Those are also not diffeomorphic quotients, because if they were diffeomorphic, then the universal covers would have to be diffeomorphic. And we know that these two manifolds are not diffeomorphic because these Kuiper invariants are different. So you even get examples with the same fundamental group that are not diffeomorphic. So that's quite nice. So what's known about the topology of these things? Well, every fake length space is homotopy equivalent to some classical length space, and there are only finitely many homotopy types, and the finite number depends on the number of multiplicative units in Z mod D. Okay, so there are only finitely many homotopy types. Turns out there are infinitely many homeomorphism types, at least in the, well, always, but in the case that D is odd. So this classification was done in the 70s using surgery theory by Browder, Petrie, and Wall. And just to show you, that, or to maybe convince you a little bit that this is non-trivial, the general case for general D was only completed about 10 years ago. So there was a problem with having two torsion in there. So it's always the way, right? Two torsion is not always your friend. And it seems that the smooth classification of these homotopy, of these fake length spaces is still open, even in the case where D is odd, where this has been known for 50 years, up to homeomorphism. So it seems that there are, that the surgery theory isn't sophisticated enough, or we aren't clever enough to complete the classification up to diffeomorphism yet. Okay, so let me now say something about the homotopy RP7s. So every one of these 7 manifolds admits a free isometric involution. And again, it's something that preserves the biquotient leaves. And so before, the Z mod D acted on the left of the first coordinate. In this case, the involution acts on the second one by multiplication by -1. And remember, plus or minus 1 commute with all quaternions. So this is an action of Z mod 2 on S3 cross S3 that actually descends to each of the biquotients and is free. And it turns out that this action of Z mod 2, together with the action of Z mod D for the all possible D odd that are allowed for any one of our manifolds M7AB, is still free. So in fact, we also get fake length spaces with even orders, which are 2 mod 4. So if I go back, so in this case, say this homotopy sphere, you get all D odd, but you also get all 2D for all D odd appearing as fundamental groups. Okay, So this involution, you can think of it as being the antipodal map on each of the S3 fibers. So if you think about the S3 bundles over S4, this is the antipodal map on the S3. So that's, if you track through from the how we construct the manifolds and think about it hard enough, you can actually see this, that it really is just this antipodal map. And it turns out Lopez de Medrano in the 60s classified all manifolds with fundamental group Z mod 2. And in this particular case, in dimension 7, he showed that, adapted to our particular scenario, in dimension 7, he showed that up to connected sum with an exotic 7 sphere, the diffeomorphism type is controlled by 2 invariants. One is in Z mod 4, it's called the normal invariant, it's a surgery theory invariant. And the other one is called the Breuder-Lifeson invariant. And you see that there are infinitely many possibilities for this Breuder-Lifeson invariant. Okay, so this is what I was saying when I was saying there are infinitely many homotopy RP7s. It's because depending on which involutions you take, you could have this Breuder-Lifeson invariant being whatever it wants to be. Okay, so if we again restrict to homotopy 7 spheres, then these quotients by free involutions are going to be so-called homotopy RP7s. And well, we don't actually know very much about them at all. So for the fiber-wise quotients of the Milnor sphere, so now we're talking just about the S3 bundles over S4 that are homeomorphic to S7. So maybe I'll just write that here. This is S3. So the involution we're taking now really is the antipodal map on the fiber of this bundle. And for these, well, they were studied already back in the 70s by Meyer. And he showed that you don't really need to go with the full generality of this Lopez de Medrano classification. You can actually just look at so these are taken mod Z, these 2 numbers. This H is the parameter in Milnor's paper. So each of these S3 bundles over S4 comes with 2 parameters. And if you want spheres, one of them has to be a 1 and the other one that's left over is an H. And so this is precisely the Eves-Kuiper invariant of the homotopy sphere. And this thing is what Meyer called the spin invariant. And if you look at, so what he actually writes it down as 2h minus 1, plus or minus 2h minus 1 mod 16, but because I want to do everything mod Z, I just divide by 16, take it mod Z. This thing is actually the first Pontryagin class, or the Euler class of our bundle as well. So this is already in Milnor's paper, I think, or the Eves-Kuiper paper. Okay, but it turns out that this is also something called the spin invariant. And these 2 numbers, up to some mod 2 ambiguity, give you the diffeomorphism type of the Milnor sphere, of the quotient of the Milnor sphere by this antipodal action. So what happens is that the Breuder-Lifeson invariant is automatically 0 in all of the situations where you're taking this antipodal map on the fiber of the bundle. And the mod 2 ambiguity is, well, imagine X is one possibility for your quotient. The other possibility is a connected sum with an exotic sphere of order 2. And how do you see that? Well, whoops. So imagine you have your connected sum with sigma, take its universal cover. What do you get? Well, you get something that looks like a connected sum with 2 copies of sigma. And so, of course, this is the same universal cover as X would have. Okay, so if you sort of think about this for a moment, you can convince yourself that this is true. And this is the mod 2 ambiguity that Meyer's result doesn't resolve. But at least in my current understanding of the situation, it seems that Tang and Shang resolved this ambiguity because they computed the Eves-Kuiper invariant of all of these fiber-wise quotients of Milnor spheres. And they showed, again, there's a sign floating around, but I think that's to do with the possible spin structures on these guys. as far as I understand it, they completely resolve it and show that the only thing that can happen is that you get one diffeomorphism type of quotient. So at least in the fiber-wise quotient of the Milnor spheres, that's 16 oriented diffeomorphism types, and you get 16 oriented homotopy RP7s. And the question is, well, for the other guys which are not bundles, do you also only get a single diffeomorphism type? That's something we need to work out. And just to finish up, I want to highlight some recent work of Jonathan Vermelinger, a PhD student of Anand Desai, who has studied the moduli space of non-negative curvature metrics on certain Z-mod 2 quotients of manifolds, in particular fiber-wise quotients of Milnor spheres and S3 bundles over S4. And he, working from the classification of Lopez de Medrano, also gets to the scenario that Meyer is in, that he can show that everything depends on just two numbers up to a mod 2 ambiguity. And again, I think that the Tang and Zhang result will resolve his ambiguity as well. But this is a very nice paper, and he shows that the moduli spaces have infinitely many connected components. So it's very nice and well worth having a look at. Okay, so that's everything I wanted to say. Thank you very much for your attention.
Thank you for this very nice talk. So maybe we can open for questions now. If anyone has a question, you can unmute yourselves and ask away.
So Martin, in the case where your metrics are again metrics on S3 bundles over S4, do the metrics differ from the old ones? Or how do they differ from the old ones? Do they have less zero curvature plates, for example?
I have no idea. So my guess would be yes, they differ. My guess would also be that the way we show it is to check isotropy groups like you did with Carsten for the SO3 action. That will probably tell you, well, at least in many cases, that these are different metrics, but we haven't looked at it. Of course, we would love to be able to say something about the moduli spaces of these non-bundle guys, and that's something that we've thought about. But the problem is that the metric we use for computing the Ilse-Kuiper invariant is not the one we use for the non-negative curvature. And of course, the Ilse-Kuiper invariant is closely related to the S invariant. And the S invariant is the one you want to look at if you're talking about moduli spaces. So to a certain extent, we have computed the S invariant to some possible integral ambiguity for a metric that's not non-negatively curved. And so we'd like to somehow build a bridge between these two if we can. So we can certainly get positive scalar curvature on this metric we use, but it's not clear how to approach it. But this is, we started thinking about this and had to break off for various reasons. But it's certainly something that's on the agenda.
Can you also get exotics S3 cross S4s?
This is also a question that we want to look at, but we've been focused on the rational spheres because we keep finding interesting examples. But this is certainly something I want to think about, because I think you and Carsten showed that you, or mentioned in your paper, that you already get many of these strange S3 cross S4 copies of S3 cross S4, and I'd certainly like to see if we get even more, so even weirder ones.
I don't remember that, but I believe you.
Yeah, you mentioned something about it in your paper.
Okay.
I don't remember what, but it's certainly weird.
All right, do we have more questions? Maybe just to elaborate on something that Wolfgang just asked you, if you just consider the moduli space for a positive scalar curvature, you get infinitely many components on these guys, just with the S invariance, the classical thing?
Well, we don't quite have the S invariant. So the S invariant would be the right-hand side of the Yield-Kuiper invariant. Remember this complicated
Right.
thing just on the geometry of M, without the mod Z condition. And it's not clear. We have to go through all of our computations again. There could have been cases or situations in our computations where we discarded integral things that were appearing. So it's not quite clear that we have computed the S invariant, but I mean, if we were more careful, it's quite possible that we have done. But this is something that we need to check.
And perhaps if you indulge me, I'll ask another question, which related to the structure of the flat planes. So you're taking a free quotient, right? It's a free action on a 10-dimensional homogeneity 1 manifold. Could it be that, like, so Chris Tapp, who hopefully is still around, perhaps had some results about whenever you take, I mean, in many situations, you take quotients and the flat planes are the same, right? You keep at least, well, you keep exactly the same flat planes as the horizontal ones upstairs. Is that, I mean, does that apply here? Is that the case here? Could it be that the structure of flat planes is just the same as the 10-dimensional homogeneity 1 Grove-Ziller metric with horizontal flat planes there?
Well, on the 10 manifold, it's, I mean, it's certainly the Grove-Ziller metric.
Yeah, but I guess
I don't know. I mean,
upstairs.
in the middle, in the Grove-Ziller construction, it's a product, right?
Right. Yeah.
And the product structure
question is the middle still totally geodesic in your example?
Well, I mean, we just take your metric and take the quotient, which is leafwise. So all you're doing is taking, I mean, you still have interval cross homogeneous space and your quotient in the homogeneous spaces. So you're still going to have a product in the middle.
So then you get lots of zero curvature plates from the Soul theorem and Perelman.
Yeah.
You have these flat strips in there.
Yeah.
Yeah, but not only that, I mean, you probably get the exact same ones, right? I mean, the question is more like the eighth answer of this quotient. Is it, I mean, does it vanish on these flat planes? Possibly.
I have no idea.
I mean, that's the proof is using some kind of estimate of Jacobi fields, right? In these horizontal directions, it could be that they're quotient out by an S3. It might be the exact same thing as just looking upstairs at a standard Grove-Ziller metric.
Yeah.
I mean, if I were to guess.
Yeah, I don't know, but certainly in the middle, it's still a product. It's a product rather than with the homogeneous space. It's a product with a biquotient.
All right. Do we have any further questions? I don't see anything in the chat. So I guess if not, we can thank the speaker again.